Hello, my name is Wyatt Rabita, and this is my Physics 2211 Lab 4 report on oscillations. This lab observes the motion of a system containing a weight, spring, and the Earth. The purpose of this lab is to explore the motion of the weight in greater detail and compare it to a model created on GlowScript. This will let us analyze if the model follows the energy principle when based on real-life motion. The fundamental physics principles used in this lab are Newton's second law and the energy principle. Newton's second law is the change in momentum of a system is proportional to the net force applied to it, and the energy principle is the change in energy of a system is the sum of the work done by the surroundings as well as the thermal energy exchanged. Initial conditions. The mass of the weight hanging from the spring is 0.402 kilograms. The length of the spring with the weight attached, L, is 0.7 meters. The initial position of the weight is negative 0.11255, negative 0.62281, 0 meters. The initial velocity is 0 meters per second as it is at rest before going into motion. To do any sort of calculations with the spring force, the spring stiffness K and relaxed strength L0 had to be found first. To find K, we can rearrange the oscillation period formula, T equals 2 pi times the square root of m over K. To find the oscillation period T, I looked at the peaks of the oscillating motion for both the x and y direction movement and averaged them. This led to an average oscillation period of 1.586 seconds, which I then plugged into the oscillation period formula to find K, which ended up being 6.3093 newtons per meter. After finding the value for K, the relaxed length of the spring, L0, can be found by using the net force formula. Since we're trying to find the relaxed length of the spring, the system is going to be at rest, meaning the net force acting on it is 0. There are only two forces acting on the system, the gravity and the spring force. For the net force to be 0, these forces have to be equivalent in magnitude and in opposite directions. Plugging in numbers we already know, the relaxed length of the spring comes out to be 0.07559 meters. Since all these initial conditions have been found for our system, we have a basis for the computational model in GlowScript. For our calculations, the variables need to be initialized, which is just a fancy way of saying that the initial conditions are being given variables to use in the future. Since I am analyzing energy in this experiment, the kinetic and potential energies have to be initialized as well. There aren't any calculations I need to perform with these because the formulas will pull from the set of initialized variables. To make the computational model work, the code uses a loop to constantly update for different variables until a certain time has been reached. First, the forces of gravity and the spring must be updated with their respective variables. The gravity force will remain constant, the force of the spring will be changing due to the s variable changing. Next, the position and velocity of the system must be updated using Newton's second law, and the net force on the system is changing. The position of the spring is updated, and the unit vector for the spring is updated as well. Finally, the different energies of the system are updated with the new variables, and the change in the energies is recorded, which will be used to prove the energy principle later on. Comparing the model, blue ball, to the observed motion, red ball, the x and y positions are very similar until they start to desync. However, the energy principle is proven to be correct in that the kinetic energy plus the potential energy is equal to 0 since there is no thermal heat exchange. What about error? Differences in the computational model and the observed motion of the spring system might be explained by smaller interactions that affect the net force that aren't present in the computational model. Such forces may include drag, interparticle forces, or heat exchange with the surroundings. The system might have also moved in the z-axis slightly, making it so that the observation doesn't perfectly match the model. What does it mean questions? For my model, the energy principle is indeed satisfied. There is no heat exchange in the model, so the change in E is equal to the work done by the surroundings. Since there is no external work done on the system, the total change in energy is equal to 0, which can be seen on the delta E over time graph in the previous slide. The period of oscillations in the x and y directions actually differed in the analysis of the motion in tractor. The average for the x direction was 1.6524 seconds, and the average for the y direction was 1.5196 seconds. These two different oscillation periods make the spring stiffness constant different as well, affecting the motion of the computational model. I am Wyatt Rabita, and that was Lab 4.